Welcome, everyone. My name is Thomas Stein. I'm the Executive Director of Guarini Global Law and Tech, and I guess I'm responsible for this operation. So if anything goes wrong, it's my fault and not the fault of my colleagues who worked really hard to put this together at very short notice. Thanks so much for coming and for being here early for our lunch that we titled, How Does Generative AI Work? And to answer that kind of question, I'll hand it over to my colleague, David Stein, with whom I had the pleasure to teach a new seminar on global tech law this last semester, that some of our students who attended might be here, so they can tell you what they thought about it. And I encourage all of you to ask them what they are working on, because they're writing really excellent papers about different digital infrastructures. And the idea behind that seminar was really to contrast how a former systems engineer and future legal academic might think about generative AI and digital infrastructures with how a former European doctrinalist and now global governance scholar might think about these digital infrastructures from a STS perspective. So bringing into conversation scholars, practitioners, lawyers, activists from different vantage points is really one of the purposes of this conference. But to do that in a way that is not too superficial and that gets AI right, we thought we would create some kind of baseline by letting Stein introduce generative AI to all of us. And you'll see he has an interesting way of presenting this kind of infrastructure, and you should feel free to ask and challenge him if you're not convinced. Thanks a lot, Stein.
So I guess I'm starting us off by trying to have a little conversation about just what generative AI is. So this is a bit an exercise in definitions, but also I want to remove some of the magic that I think a lot of people feel when they see generative AI kind of doing stuff that seems hard to explain or hard to understand. And also maybe ground us on what counts and doesn't count as generative AI. So I expect the reason we're having this meeting now is because there's a bunch of products and pieces of open source software that have come out in the past year that seem to do a lot more than AI has in the past. Text generation tools like ChatGPT or Google's Bard or a number of other lower profile things and image generation tools like DALL-E or Midjourney. There's also open source tools that I think get a little less attention, but are similarly powerful. So Koala out of Berkeley has been the base of a lot of text generation models from open source groups. Similarly, Stable Diffusion from Stability AI is a open source model that does something similar with image generation. And just an example for those of you who haven't played with some of these tools, here's just ChatGPT, what that looks like when it's running. So I typed in, I'm a presenter at this event. I put in a link. And I said, I want an outline for my presentation. And the text chats can browse the web, take a look at the conference, figure out my name and what it's on, and then say, oh, you should define generative AI, and then like do a deeper look and suggest a couple models I should talk about. And then says I should talk about the GDPR and AI Act, which I'm not going to do. There's people who know a lot more about that than me, but does something pretty reasonable, which is surprising. And it's surprising that it does so well and so quickly. So I think that's why that's captured a lot of people's imagination. Here's similarly Midjourney, which is one of the leading products on the image generation side. When I was looking at it last night, I actually saw a couple in the public free version shopping for a wedding ring. So iteratively explaining what they wanted the ring to look like to try to get an image to bring to the jeweler, which seemed kind of interesting. You can also see you can do much more richer and sort of more interesting image generation. But there's other generative AI that you probably interact with that you maybe don't think about as generative AI because you're not getting quite as close to the raw just machine as you do here. So the little people always ask box in Google is almost certainly some kind of generative AI. I believe it's running on something called T5, which is another model similar to GPT. A lot of phones, especially most Android phones, have a magic eraser that actually runs on the same technology that does the image generation things that we've seen a lot of and discussed a lot of. This is some of the wacky open source projects out there have done even more. So this is something that takes poorly drawn, hand-drawn images along with a paragraph or two description of what you were trying to draw, and then attempts to infer what the actual drawing was, and works surprisingly well. There's some other systems. So this one takes an image and creates Pokemon instead. So these are its responses to a couple famous paintings and some interesting portraits that just kind of tossed in as examples to the model to see what it would do. I think they're believable Pokemon. So this is generally, I think, when people are thinking about generative AI, the kinds of systems we're talking about. What I want to do over the next, let's say, 30 minutes is try to explain what's actually going on in the computers in a way that makes sense and doesn't do too many abstractions that are oversimplified or unfair. And that unfortunately means that there's going to be a little bit where I'm going to just be putting together building blocks that might not seem like they go together. And I think what might be surprising is that about 20 to, I'm going to go over. So I'm just going to say 30 minutes of this is going to be talking through history and sort of building my box of Legos of the different foundational technologies that are in use. And then all of a sudden in the last second, we're just going to have generative AI. Because this is something that happened really recently and builds on 50 to 70 years of history. And that's kind of how I want to structure this, just so we have some sort of thread as I put together this box of Legos, which is to talk about this as a historical thing. So just work in roughly chronological order through the history of AI development, starting in the 40s. I think am I one slide behind? Sorry about that. Okay, so one of the earliest concepts that's still present in AI today is this paper by Claude Shannon in 1948 that tries to kind of build a mathematical model around text. And the idea roughly is to take a phrase, find that phrase in a book, grab the next word, and then take the last 3 or 4 words from this new phrase, go find that 3 or 4 words in a book, take the next word, add it in. Maybe this will generate something that feels like normal text. We can do that with all of the books because I have a computer. And so I can say, how often does the phrase "this presentation is" appear in every book written in English in the last 10 years? And I can see it's not very common, but the most common word to come after "this presentation is" the word "to." And then I can say, how often is "presentation is to"? Most common next word is "be." And if I keep going, I can generate something that feels like a sentence. This presentation is to be found in the literature on the subject of the next generation. It feels sentencey. The words fit together. But if I kept going, you'd find this is kind of like mashing the autocomplete button on your keyboard. It just is gonna, each word feels like it follows the one before, but there's no common thread through the whole thing. Weirdly, kind of the state of the art for a long time after 48. So I pulled this database from of all this text from something that Google's been sharing since 2006, because this approach is still relevant. It still is kind of the foundation behind stuff like autocomplete on your keyboard. And that's been true through till about 2017. So from the 40s until very, very recently, the flip through a bunch of books, see what the next word is kind of the base for all of text generation that's happened, which is one of the reasons why text generation has traditionally been kind of crappy. Soon after that, programmable computers became a thing. So things where you can write code and run them, and you can kind of do arbitrary things. This is ENIAC, which arguably is one of the first programmable computers. With the advent of computers, there started to be this excitement about what can we do with computers. And so over the 50s and 60s, there was a long conversation that kind of imagined just computers could eventually do everything. So the Turing test is one of the first definitions of something that you might think of as artificial intelligence. The Turing test imagines a person behind a wall sending a message into two rooms, one of which contains a computer, one of which contains a person, and then looking at the responses and trying to guess which room has the computer, which room has the person. And the idea is, if we ever achieve true artificial intelligence, you won't be able to tell. You'll have no idea which room contains a person, which room contains a computer. That means the computer is doing a good enough job at emulating intelligence that we've successfully built a machine that can do things like a person can. And that's kind of the definition of artificial intelligence, is just within some constrained system, do something kind of intelligent. So the definition of AI, or at least the early one, could be basically every app you've ever used on your phone or computer, anything where you're getting the computer to do something that feels kind of intelligent, that's processing information in some way, arguably is within the scope of some definition of artificial intelligence. And obviously, I'm sure there's a lot of legal scholars in here who are going to explain how that's not the definition that's actually relevant. But it's when we think of the field, that's what it is. It's very close to being analogous with just programming computers in general. Machine learning is a subset as a subfield within artificial intelligence that focuses on how can I make a computer do the artificial intelligence thing without manually programming everything in. And even from the early days, there were kind of two approaches to this that made sense. The first is, for the sake of not introducing too many words, I'm going to call it neural networks, which is this idea of like, I'm just going to emulate a brain. I'm going to like make something that does what a neuron does, and I'm going to hook a whole bunch of them together, and it's going to be able to think. And won't that be cool? And the other camp is just to think about what you want to do and then manually program a computer to do that thing. The latter camp is basically the only one that was practical for research at that time, because building a big enough computer to emulate a brain was just not practical. Yeah, I have time to get into this. Okay. So I want to now start with building my toolbox. So the first thing I'm going to talk about is the paper that seems to have coined the term machine learning, which is this paper trying to figure out how to play checkers from the 50s. And the paper starts out by kind of saying, I can't build a brain simulator, so I'm going to have to solve something pretty focused on checkers. And then it imagines a game of checkers where there's a whole bunch of possibilities for the first move. For each of those moves, there's a whole bunch of possibilities for what the second move might look like, and the third and the fourth, and so on. And there's too many possible outcomes to actually write in every single possible game that there could be. And so instead, what Samuel proposes is coming up with some kind of scoring function. So saying at each turn, I'm going to try to guess how good that board position is. And the way he did this is he wrote out 38 different possible scores for how good a board position is. So which piece how far is my furthest piece forward in the board? How many kings do I have? How many pieces do I have left? How many possible moves do I have? He just made a list of all the things he could possibly do, and then said, I get this many points if I do that thing. And then had the computer play against itself, assuming that its opponent would make the best move according to its scoring function. But it didn't have both computers use the same score. What it did is it had the red pieces always pick a new thing. So it would only pick 16 of the 38 possible scores, and it would stack rank them. It would say, okay, like this is the most important thing. This is the second most important thing, just arbitrarily. And it would slowly change that order as it went by looking at which of these wound up being important in deciding which path to take. And then anytime it won, the black player would just get a copy of the red player's score, and the red player would keep iterating. And if the red player ever lost 3 times in a row, it would throw away everything and kind of guess a new random 16 things and start from there. And this worked pretty well. And then there's a longer discussion about maybe ways to make this better, but this is the paper that proposes sort of a framework of, look, I did the machine learning thing. I didn't write down what the answer was. I wrote down a bunch of guesses, and then I had the computer come up with something reasonable. And this winds up being one of the 3 general approaches to machine learning that's used now. So this is something called reinforcement learning. The idea being that you test something, you know what the outcome will be when you test out a new approach to an algorithm. And by iteratively trying to make it better, you can have the computer just sort of guess and guess and guess and guess and guess until it gets to something good. There are 2 other terms that are useful that I'm going to introduce here. They come a little later in this form, but they're useful to talk about. The first is supervised learning. So this is where for each input and output, a human manually marks that this behavior is good and this outcome is bad. And that's specific for training. So image labeling is an example of this, where I might have lots of pictures, and then I have a person go through and say, this is a picture of a car. This is a picture of a container ship. And then when I'm training a computer, I can say, like, did you correctly identify this or not? Because I have a human to refer against. The other approach is something called unsupervised learning, which is where you search for patterns within data. So this is just a bunch of data points, and I can say, if I want to find 3 different categories, rather than learning where rather than specifically labeling each thing about the categories here, I can instead say, just like find the ones that are close to each other, which is a form of learning. If I gave another point to that system, it might be able to guess if it's red or green or blue, in terms of whatever those categories are, just because that's the clusters it found. Unsupervised learning doesn't require training data that's labeled by a human, and so it's sometimes a lot easier to do. It can also sometimes discover patterns that maybe a person wouldn't have noticed in some large data set that has some property that's easy to distinguish between. If you think about these 2 approaches, though, the machine learning approach of big neural networks just wasn't practical, wasn't useful. And so expert systems were basically the only thing being used in practice. Though there was a little bit of academic attention on neural nets, almost all of the research and practical work from the 70s through probably the mid 90s was on this expert system approach. So one of the earliest commercial expert systems is the Mycin system, which was just a big tree of possible outcomes for treating meningitis, which is something that requires a lot of expertise. And so a group of researchers at Stanford looked at how all of the meningitis experts were diagnosing and interviewing patients used that to build basically the same kind of tree approach that the checkers game was used to build, to figure out what are the scores that I need to pay attention to when talking to a patient, and then gave that to physicians who might be encountering meningitis but aren't experienced experts in diagnosing meningitis, as a way to have, look, here's a computer that can give you sort of synthetic expertise in diagnosing this kind of complex, new, difficult to figure out the appropriate prescription disease. Yeah. This is basically what systems look like until the 80s. In the 80s, computers start to get good enough to do more complicated machine learning stuff. And so a bunch of interesting tools start coming out of academia. Some of them are put into practice. These are a few examples. I picked these for visual interest, not because they're the most relevant ones. So the ability to look at images and figure out where the stuff in the images is starts to become practical, at least in basic forms. And some really complicated expert systems for really complicated concepts. So this is SIFT edge detection, is this way to tell if different little things in an image are actually related. So this is an example of the Eiffel Tower being recognized from two very different angles, because all of the little parts of the Eiffel Tower are the same. And there's this wall of math that can figure out that that's actually the case. These things take a huge amount of effort and really intentional design to build, and they can basically only do one task. The reason I picked these is because most of the really relevant, interesting things, the papers don't have cool pictures. They just are the math. So AdaBoost was one of the bigger developments, which is a system for having a bunch of really crappy machine learning systems that can be combined into something better by figuring out the relative importance of the different machine learning systems in a way that's very similar to, again, how the checkerboard game worked, in terms of just figuring out relative scores of lots of different systems, and also the combination of those, which, like, pairs of things actually don't tell you more because they're looking at the same details, and therefore you can ignore them. Lots of work there. But there was a little, this is a slightly outdated slide. Dropbox didn't sync. There's a little bit of research was happening in trying to figure out this simulated brain concept. So one of the earlier ideas was, I can't look at an entire picture, but I noticed that when my experience looking at a picture is usually, if I'm looking for a detail, I don't just stare at the whole image, I kind of scan back and forth. I'll do this with a mouse for people on Zoom. I scan back and forth. And maybe I can do that with neural net too. So I'll just look at little sections of the image one at a time and scan the whole thing back and forth looking for stuff. Interesting idea. Lots of sort of mathematical modeling, no practical application. Later in the 80s, there was some work making neural nets a little more practical in terms of how do I get all of the nerve cells to actually do something useful and work together. The seminal paper came out of NYU, so I'm just gonna call that out, like Yamaku, NYU. I think it was 85, 89. Sort of demonstrated some ways to make training neurons practically useful. But again, scaling this to a place where it would actually be practically applicable really wasn't a thing. This is where I'm going to build the next piece of my Lego set. So this is the basic idea behind neural nets. What we want to do is emulate a brain. We obviously can't do that. There's way too much physics and things we don't understand. So what I'm going to do is simplify the idea of a neuron. This is too complex. This is about right. So my idea is I have a bunch of things that receive signals from other similar things. form some weighted sum of those. So some signals are negative, and I count them against my score. Some things are positive, and I count them towards some score. And if my score is greater than some threshold, I say I'm active, and I tell other neurons down the line, like, hey, I'm active. So let me show you what this might look like. There we go. Pause. Okay. Is this on the screen? Great. Okay. So this is a picture of a handwritten 5. This is actually from that original paper on making neurons practical. This is a re-implementation of that paper, if you're curious. And what I want to do is treat each one of these dots as if it's a neuron. So I'm going to say if it's black, it's not active. If it's white, it's all the way activated. And if it's gray, it's some ambiguous state in between those two. And then I'm going to put a whole bunch of neurons, connect this to a bunch of neurons. And the green here are things that count as positive score. The red are things that count as a negative score. And I'm just going to make rows of neurons, and I'm going to connect each row to all of the neurons in the previous row. So if you look here, since there's a whole bunch here, each of these neurons has a whole bunch of things to multiply by. But in the next row, there's only 8 things in the previous row. So I just have 8 things to multiply by. And that's the little green and red things here. The trick to making these learn, and if you don't remember this and it doesn't make sense, don't worry. I want you to hear the music, not the notes. The trick here is each time I see a number, so here's a 5, I know it's a 5. I can see that on the other end, my last 10 neurons here, each of which is supposed to only activate when it sees a 5, just isn't working. It's basically putting out random numbers, which makes sense because I set this thing up with random numbers. But if I went through and looked at every single one of these little pieces of green or red static, and I increased it a little and I decreased it a little, one of those is going to make this less wrong, and one of those directions is going to make it more wrong. Where wrong, I'm going to define as if it's not the right number, that should be a 0, and if it is the right number, it should be a 1. And so I can measure my wrongness, and I can also measure which direction I should move that number in. And if I just go through every single value and move it a little bit in the right direction, in the less wrong direction, iteratively, then after a couple million runs, and I pre-trained this, so think of like a cooking show where they like put it in the oven and then take out one that's already cooked rather than the oven magically doing that. You can see that I've run this for about 10 minutes, and it can tell like this is a 7, this is a 3. Here's an interesting case, though. It's confused about a 4, which is actually what I wanted to show you, but let me find a better 4. Here's a good 4. Okay, so here's a 4 that it thinks is a 9. But we can investigate a little bit and see what it's looking at. Oh, wow. This thing did a very bad job of training. I might not be able to. The idea I was hoping this thing would learn and I could show you is, here, we'll look at 0. Wow. Thought I could run this right before showing it. Okay, so here's a 6. We can see which neurons activated, and I can't really look at the static and figure out exactly what it means because the thing we learned is somewhat inscrutable. But if you squint, you can kind of see that it's looking for, it's counting more points when it sees stuff drawn in these places, and it's not counting these systems up here that are probably looking for like a 1, are looking for more of a straight line with nothing on either side. Which means if I add some lines, you can actually watch some of the neurons activate and deactivate as I make changes until it becomes convinced it's something else. This thing seems not to have learned 0. I should have trained it more. This is the general idea. You can build these things, you can train them, the longer you train them and the more you iterate, the better it's going to be at recognizing things. If I gave this another 3 hours, it would probably be really good at reading handwriting. 10 minutes was not enough time to train these systems. Cool. There's a couple of useful things you can do once you've trained an AI. And these wind up being really important in building generative AI. So the first is, once I've trained something, I can use those weights, those already trained neurons, to do other stuff. So you could imagine, if I have something that already kind of knows what to look for in numbers, I can maybe add some more at the other end of the network and be able to recognize letters more easily, because I already know a lot of things about just what text looks like and how to differentiate between text. So here's a system that I've trained to only know odd numbers. This one is trained a lot better. You can imagine, if I add some extra weights, that I can probably train this in real time and have it learn how to recognize even numbers as well, because it has a whole bunch of extra neurons here, and it has a whole bunch of extra training data, but it already knows what most of the odd numbers look like. So it knows to look for a loop at the top of an 8, which is going to help it look for, sorry, it knows how to look for a loop at the top of the 9. So that will help it look for a loop at the top of an 8. This winds up being a really powerful tool. And when we talk about GPT, the P, which stands for pre-trained, is about this idea of already having a big chunk of your network trained before you get started. Cool. That's all I wanted to say about machine learning. And that's basically all machine learning was. Neural networks was a fun academic project that didn't really have any practical applications. And there were these super complicated, very specific models built to solve very specific tasks. So like a face recognizer only recognizes faces, and a thing recognizer that knows how things scale in different ways is just really good at that one thing. In 2012, Alex Kravinsky and Jeff Hinton wrote a paper that's often referred to as AlexNet, that proved that essentially demonstrated a way to make neural nets practical. And this was a really big deal and really surprising. This is a measure of how good this current state of the art is in recognizing images. And what you can see is leading up to 2012, we could basically, the best systems we had at recognizing general images, like this is a fire truck, that's a cat, somewhere between 70 to 75% accurate, and kind of inching together 1% a year type improvements if there was any improvement each year. And all of those used very task specific, just combine a bunch of task specific things with boosting. The 2012 paper just blew everyone out of the water with a very simple neural net that was super generic. And this was really surprising, and effectively started the field of deep learning. And perhaps even more surprising is that it used a bunch of pre-existing innovation. The idea of just slide something around, the AlexNet paper, all it does is say, do the slide around trick with the recognize a box of things with a neural net trick. Just do those both at once, which was not a new idea. This is like 1980s technology. It wasn't even a new way to implement the idea, really. There was a couple tricks to make the neurons learn faster and a little bit better. But the big insights were just do more of it, just more layers. Just if it's deep enough, it's going to learn. And it learns really well. This was amazingly good at recognizing images. But also, since this is 1980s era technology for a lot of the insights, essentially all of the tricks are just how to connect those networks together. So this diagram is actually a map of the GPT, a part of the GPT system. And all of this yellow stuff is just math, just straight, like add numbers together, take the average, like high school algebra, maybe middle school algebra level math, like not something complicated, not something computery, just tricks for connecting stuff together. And these blue things that say linear on them are just the thing I just showed you, like the 1980s era, like very simple neural net. The trick is just how to combine them and how to kind of mix data around at the different layers. And you can see this in the way that the AlexNet paper presented their material, which is, this is just how big the little slidey thing should be. So this should be a 5 pixel by 5 pixel slidey thing, and then a 3 by 3, and then another 3 by 3, and then another 3 by 3, and then just a big layer at the end to convert whatever I just did into labels. So straightforward in terms of implementation, but very surprising in terms of capability. And this is a huge culture shift for computer scientists, because up until this point, everything we did with a computer was like written by a person. You'd sit down, you'd write some code, like maybe you made a mistake and there's a bug and the computer does something surprising, but it's surprising because you screwed up, right? This isn't like you're following a recipe and it's met and like it goes wrong or right in some way. This is following a recipe and use salt instead of sugar type mistakes when you see some weird outcome. You know what you did wrong. You like have a pretty precise way to track that. The idea of just guess and check and see what works, and like maybe if I stack more layers, it's gonna like somehow magically do the thing better. I like get the mechanism behind it, but I don't really get exactly why one thing outperforms another. I just know how to combine them well, is not how computer scientists thought of themselves. Like when I was in grad school, when we didn't learn neural nets because they were an irrelevant backwater, it was considered basically a field of math. We like sat with the math department. The idea of kind of try a bunch of stuff, and we know the mechanism, but we don't exactly know why, and it's not super easy to predict what works and doesn't, was not how a mathematician field thinks of itself. But it is how a lot of other fields of science think of themselves. So like this is kind of standard in the pharmaceutical industry, right? Like I know which protein I want, and I vaguely know how proteins fold, but I like can't predict it. So I'm gonna need to try a bunch of stuff, and I know where to try, and I know which experiments to do, but there's some amount of just try things until I get the outcome I want. And sometimes outcomes are surprisingly good or surprisingly not good. That's what AI looks like now, but it didn't before 2012. And so if you see, there's a lot of students and academics here who might want to cite a paper from 2010 about what a computer's capability is. Our understanding of what a computer's capability is fundamentally changed in 2012. And the field of play with neural nets didn't really exist before then. And there's a bunch of cool things you can do when you're just thinking about this in terms of how do I define how wrong I am so I know which way to wiggle, and how do I lay out all the different parts. So one of the first examples of a way to make something that does generative, I wish I'd shown examples, but if you've ever seen This Is Not a Person that generates a fake person, that's really convincing photograph, this is the technology behind that. But one of the tricks I can do is I can say, I'm gonna have two AIs next to each other, one of which generates an image and one of which gets a real image and a generated image and guesses which one's fake. And if I train both of them together so that the real one gets points anytime it tricks find the fake one, and the fake one gets points anytime it's correct about which thing's fake, they'll learn together. Cool trick to make things generate stuff that looks real. But it's important to note that the generator is the only thing useful there. The whole rest of the network, it just exists for training. And so you have this huge machinery that does lots and lots of work to train a little part of it, which I then carve out and can use for other stuff like generating images. Another trick that's useful is something called encoding. So the idea here is I take a, let's say, a picture or a piece of text, and I run it through a network that pinches into a really small point and then re-expands out. And I say, give me back the thing that I started with. And what's useful about this is in the middle, I get a nice succinct blob of numbers that represents what the original input was, because that blob of numbers is the only thing that the decoder has to try to get back to the original image. So I can show you an example of this. Here's the same network before, but now I've pinched it, so it has to somehow represent what's been written in just two numbers between 0 and 1, or I think between -1 and 1. And I've made a little plot down here where I can put a couple numbers into the system and see the x-axis is that first number, the y-axis is the second number. What you can see is with a couple hours of training, this thing learned to kind of cluster all the numbers together. So here's all the ones over here. Here's the 7s in one area. The 5s are clustered over here. This is like how facial recognition, for example, works. You just turn faces into, you say similar faces should be together somewhere if they're the same person. This is also how you turn text into numbers that a computer can deal with, which is useful for generative AI. The third trick, and now I'm literally just building the Legos so we can talk about how generative AI works. The third little trick that I think is interesting from this era of experimentation between 2012 and 2017, it's really small period of time where a lot happened because we suddenly knew there was stuff here to look for, is this idea of diffusion. And so the concept here is I take an image and I add static to that image slowly. And then I train something to try to say, what was the static I added, and remove that static. And the way I train this is essentially the same as an encoder. I start with an image, I add a bunch of static, and then I say, can you remove the static? And what's cool about this, if you look at the bottom, this is one of the images from the paper, is if you give it just random noise, it's going to come out to an image that's kind of like an image in the paper, or kind of like one of the images you trained it on. Now, telling it which image it should draw, separate problem. You would need to give the thing some sort of hint about like, hey, this static was originally, a frog or a plane. And if you don't give it that hint, which the original implementation doesn't, it's going to look at the static and just randomly draw a thing similar to things it's seen before. This is still really useful for generating fake faces or fake images if you want to do that kind of thing. All of this only works with images. The trick of slide something around, kind of scan for what you're looking for, is one of the really fundamental things here. To the point where educators, this is a popular AI course on YouTube that is quite good from 2015 that has an entire section on like why computers can't do language at all. Language is impossible, which is interesting because that almost certainly stopped being true within about 1.5 years of this being published. The best approach we had was to kind of try the slidey thing over again, but say, along with telling me what the next word is, also tell me what you would like to remember about the previous thing that you saw. And the reason is because I can slide around an image and I can say, find me a face, and I don't need to worry about the rest of the image while I'm looking for that face. But when I'm reading text, I need to remember the whole history. And so I need some way to store memory. And the problem here is there's no way to train this system unless you give it an example where you let it have as long as it needs memory, or else it's not going to learn to remember things because we're not going to be able to test it on stuff where it remembers. In 2017, basically the same thing that happened with images in 2012 happened with text, which is, this is the same progress. These orange dots are using a non-neural net approach. And you can see sort of suddenly in 2017, everything changes. And the idea here was something called the transformer, which is used for translation. The big insight for transformers is that words are related to each other. And so rather than defining a word as just a word, you instead define it in relation to other words. So this is an example of a transformer trying to translate from English to Spanish. And you can see that because Spanish is gendered, the word mucho is actually more interested in the noun that it's referring to than to the thing it's being translated from, because that's an important part of deciding which word you're going to use there, mucho versus mucha. If you tell this to look for more patterns, essentially the equivalent of putting more neurons looking for more patterns in the image thing. If we do that to look for more complicated patterns in text, it turns out to be really good at finding those patterns. And this is surprising. The paper that describes this was trying to do English to German and wound up just being able to throw this at basically any language task and having it do a pretty good job. And the trick that they did was, rather than going English to Spanish, like I showed in that last picture, they try to go English to English, but they remove a couple words in training. And the reason this works is because it figures out the links between different words in text. So for example, the word "it's" in this sentence is referring to law. Law is the thing that "it's" refers to. So the purple neuron block seems to have learned how pronouns refer back to something. There's also an orange block that seems to be learning about which things a noun refers to. If I just have a whole lot of these, I can learn a whole lot of relationships. And just like that static was a little bit inscrutable, the precise semantic meaning of these relationships is a little bit inscrutable. But the application of it is pretty straight. I wouldn't say straightforward, but I think it's relatively intuitive. Imagine we had the word chevron in a sentence. What does chevron refer to? It could refer to a company named Chevron. It could refer to a type of glyph, a little like nested arrows thing. If you're in certain parts of Canada, it could refer to the ridges on a sidewalk that visually impaired people run their cane along to know what's going on the edge of the sidewalk. It could also refer to a famous Supreme Court case. The traditional encoders would encode the word chevron as essentially the same set of numbers. I write an encoder, it encodes words. It says these are, I can't tell the difference between these words, these are a word. If I start to know about the relationships, I can maybe say, actually, for the sake of translating or managing text, these are 4 distinct words. They might as well just be different words. Maybe in other languages they are, because this is from a translation basis, that's something that makes sense. If you were imagining translating the word bakery into French, there'd be a question about, like, is this a bakery for pastries? Is it a patisserie? Is this a bakery for bread? It's a boulangerie. And maybe I could build something that tells from context when I'm saying bakery. If I'm encoding that in English in a way that keeps track of those details, then translation is going to work, but maybe other things are going to work as well. But if I did this again, so I took those words, I said, those are distinct words, and then I ran the whole thing again, and I said, actually, when I say Chevron, the gas company, am I talking about an individual gas station, or am I talking about the major corporation? If I'm talking about Chevron, the Supreme Court case, am I talking about the Supreme Court case? Or am I talking about the legal standard that it stands for? Those are distinct things. And so I could run the system again, and I could say, those are different words now. Those mean different things. And if I just kept doing that over and over again, no, add more differentiation between these different words, that find different ways that they're distinct. In the same way that I can add more and more neurons on an image to recognize an image, I can add more and more of these, they're called transformer encoder decoders, to this sentence, and I could really expand words to the point where if I see something that says knight, I could say knight is in this case referring to a chess piece on the 5th move of a game of chess, which has the following rules because they're playing the traditional variant of chess that has this specific move that's like the best next move, and that knight was not a good move, and maybe there's some reason for that. And I could say all of that is part of the definition of this word from this big system. Maybe. I don't know. It's hard to read these things and reason about them. But if I add a lot of layers, perhaps I can really separate the meanings of these words out and really embed the context from all of the other stuff in the sentence. And I can use that to build context around a sentence. The trick in the first paper was to then take that context and then just say, basically using that context, predict the next word and the next word and the next word. Never change the context. We have the context, just add words one at a time. And that's useful if what you want is a system that takes an English sentence and outputs a German sentence. You don't need that if you're trying to do just English to more English. And so systems like GPT tend not to have the separate generate context from the generate content. Instead, they use a couple unimportant tricks to make sure that context stays the same as it goes. So that's kind of it. The trick from 2017 about transformers gives us the ability to generate things. And if I spend those hours training, or in this case, months or years of effective compute time training, I can have something that does the understand English part pretty well. Where understand, I do not mean to anthropomorphize, I just mean like have a good representation of English. And then I can do useful stuff with it. So this is just the training tests they use there. So I could take that thing and I could fine tune it. So imagine if I had my system just trained on odd numbers and I wanted to add even numbers, do the same trick here. So take that thing that kind of represents English well and say, okay, but I want it to do a specific task. I want it to, I don't know, chat. I can take that original model and turn it into a chatbot. I could also say, you know what, this is a great way to build text for my diffusion model. And so I'm just gonna cut out the part that builds a dense representation, just represents English well. And I'm gonna use that to give hints to my thing that diffuses, that undoes static to generate images. And that's why you see such great image generation coming out now when it wasn't before, is because the text commands going in didn't really exist to give a hint to the computer about what it's supposed to be drawing. But if we have this really rich understanding of what you meant, or what you probably meant when you wrote that sentence, it's going to do a better job. There's a bunch of terms that just, if you hear them, artificial general intelligence is reference to the idea that one system can do a whole bunch of things. Stochastic parrot is sort of this idea that a system is doing the dumb thing that I started with of just probabilistically guessing the next word and the next word. There's a question here about world state, which is at what point is my understanding of each word so rich that I actually understand what's going on in the world, or I've represented what's going on in the world in a complete or somewhat complete way in the model. Hallucination, if you think about how this system works, the only way something like GPT knows what to say is because the representation of a word is so rich, it knows that thing. You could imagine putting that into the context instead, but if it's not in the context, then it has to guess and just do something reasonable, which is where you're seeing random hallucinations come from. And I want to leave with this, which is the question of alignment. Alignment is the task of trying to make an AI do the thing you actually wanted it to do. And the problem is these systems, we don't fully understand why they work. We can't predict what they do. And so we have to build rules around them for setting their goals, right? The idea of like, what is bad so that I know which way to wiggle my weights in the internals of the system. And that's not something we're good at as computer scientists. This is new stuff for us. We're less than 10 years into this field being a serious area of study. But it's something where the legal community actually has a lot to offer because you are used to regulating big systems that have weird emergent outcomes. And so Jan LeCun is one of the sort of inventors of a lot of the technologies here. He's largely considered one of some people I think of him as like a father of modern neural net AIs. And his argument for how do we figure out how to align this thing is essentially like we should find someone who knows corporate law because like those are big complicated systems and yet somehow we build rules for them. And so as I want to leave with the idea of as we think about the future, we're looking at prototypes. We don't know exactly how they work. We don't know how to constrain them, but we know a lot of their initial capabilities, even if we don't really know what they're not capable of yet. And there's a lot of things we can do to regulate those systems, but there's also a lot of experience in this room and rooms like it that I think could be directly built into the systems themselves. Cool, thank you.